website, what they send around.
About magnetic imaging for chiral superconductors.
Okay, thank you. Okay, good morning. Maybe everyone get a coffee. Okay. Now, okay. Refresh the mind. I hope so. Okay, yeah, I'm Yusuke Iguchi from Stanford University. So, yeah, I'm talking about our magnetic probe microscope measurement on the chiral superconductor and also the recent observation of the fractional Un-Quantized Vortices. So let's thank our collaborators first. So I work with CAM model for 7 years. Since I was postdoc in her group, I still work with her as a staff scientist and use her scanning slit microscopy for this talk. And thanks collaborator for characterization of the samples, the turbo and the badin for the potential level 1 to 2, and the pre-trail, the low thermal screw for UT2, and the theoretical collaborations with Ego, that's also for the fraction vortices, and the non-fret and the postdoc for the edge current calculations. Okay, so my talk and it's a quadrupling. It's the electron state is connected to with a key component of the March component superconductor. For a single component, as you know that in the superconductor, the broken the U1 symmetry and the two characteristic lengths, transition depth, magnetic field, coherence length. So for the March component, it's more complicated because of the March order parameter, like March band or spin triplet, and then the broken additional symmetry, like time versus symmetry, the lattice rotation, spin rotation, this Z2. And for famous March band, 2-band superconductor MGB2 has a 2 gap and has additional length scale. The coherence length is characterized for each band. And for some short range, like D vector domains or chiral domains, or each band face different certain Lorentz dynamics. So it's very complicated nature is introduced by the March component superconductor. I have shown some example of the unconventional vortex state in the March component system. This is well-known the March grain, the cuprate measurement, the 3 crystal junctions. It's a same film. The cuprate has a different crystal orientation. So a very special design system. This is zero field scanning slit microscope measurement. John Cartwright down, and so it's naturally get the pi phase winding around this point. So then see that the half integer fraction vortex is stable at this point. So it's a strong evidence for D-wave superconductivity. Okay, this is a beta degradation method to visualize the vortex. It's like a clustering in the MGB2. It can be understood by combination of two interactions, vortex-vortex interactions. The short range repulsive and the long range attractive. One explanation is that in the March component theory, the one band has a type 1 like of coherence length compared to the penetrative depth. The other band has a type 2. That is so-called type 1.5 model.
Sorry,
yeah.
when you say this is same sign vortices, that potential is for same sign vortices?
So
That UVV.
so this one.
No, the potential you draw upper right.
Here. See the interaction that's
Interaction between two same sign vortices.
Yeah, right.
Same
yeah.
sign.
The same sign, yeah. Right. Yeah. So for the type 1 like attractive interactions and type 2 like repulsive interactions. And it's a combination of these two types that there is a local minimum. And it's this determined that what's the voltage cluster distance.
Okay.
Yeah. And okay, this is a highly anisotropic layer superconductor, the cuprate case. And that's split this vortex like this. So it's randomly split because it's very highly anisotropic. It's easy to split by applying the local field, like a scanning Hall or scanning slit microscope. It's only happened in very highly samples. anisotropic sample. But in theory, they expect more fraction vortex or magnetic phenomena in the large component superconductor. Yeah, as Igor said this morning, his theory predicts the fraction vortices in the general, more the large band superconductor, the bulk superconductor, and the same analogy with the chiral superfluid. The chiral period, the spin-triple superconductor predict the fraction vortices. There is an indirect measurement, the strong to hallucinate, where the distance of radium is a half height jump, the magnetization in the ring shapes, but there's no real observation of the fraction vortices in the real space measurement. And for chiral superconductor, they also expect chiral edge current. I will talk more later. But for example, the polar current measurement detects a spontaneous magnetization just below Tc in strong hallucinate or the uranium superconductor, the many samples. But also, there's no direct imaging of this to the fraction vortex and the chiral edge current. So today I'm talking about two samples. Potential very 1 to 2 is the candidate of the S plus IS, and UT2, this is a spin triplette and the candidate of the chiral period superconductor. Okay, so here we use a scanning script microscope. Our script is a small pickup group in a square circuit, and it has a gradiometric structure, so it's a cancelled uniform field. And also there's superconducting shielding. So only the magnetic field goes through this pickup group. And then locally visualize the vortex field and detect the transition depths, or measure the magnetic field from the current. It also has a concentric field coil. So apply the current through the field coil, then we locally apply the magnetic field, and then we detect the local susceptibility, and then it also gets the transition depths or local. Okay, let's first. So as you know that in the bulk superconductor, magnetic field is a quantized, the average vortex. So I need to again do some better. I think the wave function, size, and with the quantum phase, and total current can be written the two terms, the phase winding terms and the vector potential, and then calculate total flux in the vortex is integrate the vector potential around the path, and if it's enough far from the vortex center, then z equals 0. Then we only need a phase winding. Only for the quantum conditions, this is the integer, so we get the integer quantum vortex. And in our measurement, so we see this magnetic flux is localized in the point of the vortex center. For the March band case, it's more complicated, as Igor said this morning. So he's calculated this total current for all bands, Fermi energy, and for this is a simple model for two band. There is N1, N2 is the integer of the phase winding, but if it's a N1, N2 it's different, there's become a fraction. For example, it's N1 equal 1 or N2 equal 1. There's a different fraction vortex, but the total flux is still quantized. And if the psi 1, psi 2, all the parameters are different temperature dependence, then it's also this value is temperature dependent. But since 2002, there's no direct observation in the real material. Okay. So our group measured many kinds of multi-band superconductor, but we've never seen the diffraction vortex. But here we focus on this material because by the measure time versus symmetry breaking by MSL, then it suggests the S plus IS state is stable because of the flux ratio is the maximum around this region because of the lifted transition from the 3 band to 2 band. They also measure fluctuations in the nearest measurement and suggest a quartic metal. So if it's true, like it's originate from the very moderate interband interaction, then maybe also fraction vortices is stable. That's our basic motivation to measure this one. So after bodying down the mirror sound measurement on this sample, we get many crystals, and they creep to the one surface, and then scan these 4 regions. It's over the 100 micron scale. Okay, so I already showed that the the integer vortex is observed in this material. But when I change the color scale, there's a tiny signal there. It's like a fraction vortex, but it's from this one, it's very difficult to distinguish that it's just a magnetic impurity here, even if it's just a dust in the screen of my computer. So I repeated the measurement, the field occurring, and then, yeah, in the different summer cycle, we see the different fraction vortex-like object. Like a higher field, this other integer vortex magnetic field is overlap each other, and we could see. So then let's think about let's check if this is a fraction vortex or other something. So I make a 3 checklists. It's a mobile object, and it's estimated the flux is totally quantized or the fraction, and it's checked the universality within this sample for the temperature dependence also. For the mobility, yes, it's very obvious. It's a mobile. While cooling or heating, then hop to another pinning site. And when I apply the magnetic field, and easy to manipulate location. So it's obvious a mobile object. So this is a vortex, not like pinned in the very special location like a tricrystal junction or some of the specific magnetic impurities. This is a vortex. And so because we can manipulate the location, so we try to manipulate the locations under exactly the same as the integer one and the fractional one, small one. And yeah, it's successfully we can manipulate so that this small object, small vortex, doesn't need a special locations, even if it's the same with a conventional vortex. Okay, then let's estimate the flux. Okay, so yeah, there's a different summer cycling with a positive small vortex, a negative, and an integer vortex. Here I first use a point source model fitting. Put the n-finite monopole deep inside the sample from the transition depth, and then calculate the total flux through the pickup loop, and then calculate the transition depth for this temperature. Because of the same temperature and the same locations, I use a fixed transition depth and then get the number of 0.3 or minus 0.3 for this experimental result. Oh yeah, so this is a fraction number, but here I still use this assumption. So I also try to just simply integrate magnetic field. So this is a little bit rough estimation, but I still get a similar number for the positive one and negative one. So yeah, this small object, small vortex, carry a fractional number of the flux quantum. So let's call it a fraction vortex. And okay, but temperature dependence is more dramatic. So this is a cross section of the integer vortex. Yes, as from the DC, and the lower temperature, the magnetic field is more localized because the penetration depth is shorter in the lower temperature. And yeah, the peak height is increased in the lower temperature. But for a fraction vortex, as a completely opposite temperature dependent, the cross section is like this. The higher temperature has a stronger peak. It looks like a disappearing. And here, I use a same fitting, monopole fitting model, it doesn't work. It means that the delocalization happened for this fraction vortex. This is consistent with the Marchband model, as Igor mentioned this morning. Okay, so here I measured a similar procedure for the different locations over the 100 micron scale far, and then estimate the fraction, then see the very consistent temperature dependent. So this fraction number is temperature dependent, and I think depends on the material parameter. And after publication, the Jun and Patrick called this is an Un-Quantized vortex. So we use this term for this vortex. Okay, and after our publication, there are two validation works following our work. One is a similar scanning squid measurement, that UFO1 group. They use a very similar doping level sample. And they also saw the fraction vortex and the conversion vortex. In addition, they observed the splitting from the single vortex to the two fraction vortex across the TC. This is exactly expected by the theory. And the total flux is condensed. And for the STM measurement with the different samples, doping samples, they also see the fractionalization across the TC. This is we have a talk in this session later. Okay, and for the theory that from the Igor's group, the 3-band S plus IS model, now we explain this temperature dependent, the fractions, use a very similar but a little bit different temperature dependent of the gap.
Actually, it's not technically from my group. I think Julien
sorry.
did this calculation. He is already professor.
Oh, yeah. Okay, yeah, so let's compare with the existing model and our experimental result. For the half integer three-crystal point D-wave one, it's obvious difference for the mobilities and temperature dependent. For pancake vortex, it's mobile, but it's temperature dependent and the delocalizations not consistent with our case. And also our material is not so highly anisotropic, so yeah, this is not our case. And 2D planar defects get the similar delocalizations, and yeah, also if it's a very complicated 2D planar defects, maybe it also looks like a mobile. And after our publication, Prastovets and Balsin proposed using this model, explain the temperature dependent also, like pinning locations is very temperature dependent. Lower temperature very close to the more to the planar and then the more delocalized. But still, it's inconsistent with this term because of there's always a 2D planar defect there, and when the vortex close to that defects, then always that the vortex should be very delocalized. But in our case, we see that the integer vortex and the fraction vortex are the same location, the different Green cycle. It cannot explain with this theory. And so now that we only have a Marchband model, we explained everything. But still, we have more work, to microscopically explain the delocalization of this one and the doping effect also. Maybe that the S plus IS domain war is the key, but yeah. So maybe that the STM measurement talk is may explain this one. And we don't know that how to make a fraction vortex and convergent vortex which is a favor at the same locations. Okay, so how many?
9 minutes.
9 minutes, okay, yeah. Let me quickly show it. Current measurement in the Chiral superconductor. So in a Chiral superconductor, it also characterizes the topological number same with the topological insulator, and there's a chiral current predicted. For example, chiral P wave, the Matsumoto algorithm calculate a spontaneous field for the storm to resonate, and that signal is much larger than the noise level of the scanning Hall or scanning squid measurement. Then our group and other groups measure storm to resonate and other samples, but we've never seen the chiral current, even if our noise level is much smaller. So every time we explain what's the upper limit of the spontaneous magnetizations, or we estimate what's the upper limit of the domain size, smaller than our spatial resolution. In the chiral split, superfluid, chiral domain is observed in the real space in the millimeter scale. It's very large. So if you have a better spatial resolution or have another crystals, then we hope we can still measure chiral domains or chiral current in chiral superconductor. And now we get the new candidate, the chiral superconductor, UT2. This is a spin triplet. State is suggested by the many nice shift measurement. There are several types of measurements such as the chiral superconductivity, the Chiral groups and experimentation depths, and the chiral state observed in the STM. This is not the chiral current, this is the edge state. So asymmetric signal. And for local measurement, the Aron-Cattoni group and specific heat measurement show that the multiple superconducting phases are high hydrostatic pressure, but it's also including the ambient pressure. That's so we are interested in this material and started to collaborate with the Rosarno's group. But at the same time, they improve the quality of the sample. Then they higher TC only show the single phase transition. So we get this cleaved sample. It's the same batch with this crystal. Then susceptibility measurement near TC shows very clean single phase transition, and there's no kink below TC. It's obvious this is a single phase transition. We also measure the superfluid density at low temperature. This is consistent with the point node or very small local minima along these directions. There's a consistent with anisotropic gap in the sample. We also measure the vortex. So this is a high field cooling and zero field cooling. There's two kinds of interesting points. One is a vortex looks like a pinned around the one direction. This is a parallel to the crystal edge. And the other one is zero field cooling still have a vortex and anti-vortex. So it suggests there's a local magnetic source, but above TC there's no visible magnetic field from local field there. For the vortex spinning, also UFO1's group work with Daniel and Igor's measured a similar type of the pinning recently, and they proposed can explain the anisotropic the vortex-vortex interactions different, like anisotropic type 1.5. So maybe this can explain this one. And then for each vortex looks like a very quantized. It's not fractional. Here I plot the magnetic field trap in the vortex, number of the vortices multiple with the scan area, plot against the applied field current. So it's a linearly increase, and there's no evidence for the fraction vortices. But there's small gap there. It's a 0.01, else that is very small. We suggest there's some possible internal field. And it's still consistent with other squid measurement or the NMR. So there is some mechanism to enhancement of the local magnetism inside a superconducting state. Maybe the impurity is the key, but we don't know the exact theory to explain. So here I focus on the edge state, the zero field cooling. We see the magnetic field as a peak structure along the edge over the 50 or 60 micron scale. This looks exactly the what we expect for the carriage current, but it's much larger. And okay, this is cross section, the magnetic flux, and this is a 4 mil pi naught, and this is consistent with the Matsumoto-Stiglitz model. And then increase the temperature, and this peak disappear just below Cc. And this can be fit with the phenomenological theory, the magnetization in the superconductor. But our question is that this magnetization is intrinsic magnetization or some extrinsic origin. Because there's some negative measurement for the intrinsic merge components to the conductivity. One is a specific heat and hour scanning skit only detect a single phase transition. But yeah, we expect the multiple for this crystal symmetry. And the higher TC sample, there's no higher symmetry breaking in the μSR and polar measurement. And it's a STM also. Yeah. So then we need to think about impurity model, like extrinsic model, because impurity model may explain why we only see this time graph symmetry breaking in the lower TC sample. But what's the existing model may explain? There's two examples I get from this review paper. One is a local supercurrent loop around the non-magnetic impurity, so like S plus ID, but it's only they calculate for the D-wave case. So we cannot simply apply this one for our case. The other one is the enhancement of the RKKY interactions around the magnetic impurity. So it's a state is a YSR state here. And this enhancement only happened in the superconducting state. So then there's a distance, if you change distance, then there's a RKKY interaction that favors the ferromagnet to antiferromagnet. If it's ferromagnet stable, only in the superconducting state, then we get the spontaneous magnetization. But we still don't have any microscopic model for UT2. Okay, let me summarize my talk. From our measurement, we see the fractional, Un-Quantized vortex in the March-1 superconductor. And we don't see the spontaneous half-integer vortex, but we see the H current, the H field there, but still it's possible the extrinsic origin. So yeah, thank you for your attention.
Yes. So in Shanghai Jiaotong University, the new data shows that some kind of a chain, like along the chain, many fractional, looks like a fractional vortices there. So do you see such things or not?
Okay, yeah, that's a good question. So they see that the vortex core, so that the So, but we only see the magnetic field. So the magnetic field is much stronger from the integer vortex. They overlap each other, and the fraction vortex is always much smaller than the integer vortex. So we couldn't resolve these many boxes there. So we only apply the very small magnetic field.
I see. Feel that different. Okay.
Yeah, actually, I think it's actually not inconsistent because of you also see some stripes of magnetic fields in some regions, and this may be the change.
The boundary.
Yeah, because simply the distance in Shanghai Jiaotong, the distance between vortices is very, very small, much smaller than that.
Yeah, feel that higher. Yeah, okay.
Hans?
Do you have sufficiently many of these fractional vortices that you can say something about correlations? I mean,